In this video, we are going to write the software that detects the voice and zeros on the DCC signal. First, we are going to talk about our circuit diagram for a detector circuit.
Okay, so this is the circuit diagram. We have a PIC microcontroller, which is the 18F25Q10. We have an in-circuit programming socket, which connects the PIC kit 3, which is what we're using. So that's connected up. The power supply was just 5 volts coming in there. This resistor and diode just there to show that the supply is on. This decoupling capacitor is right near the chip, and this is just a general supply ripple capacitor. We have an indicator here which is driven by RC3 output pin on the microcontroller, and we have an RS232 output which comes out of RC6 on the microcontroller, and we just put a resistor in series just in case we short things down by mistake, so it protects that pin. Then we actually connect the rail input through these 2 resistors to this opto isolator. So this light emitting diode triggers this Darlington pair, which just pulls this resistor down. This little circuit here just filters out some high frequency noise if there's any there, and then the output is gone through another resistor there to limit any accidental shorts and things, to the input pin here, which is RB5. Now RB5 is also the input pin that can be used to trigger the timer 1, because timer 1 can be used as a gate function, and the gate function, it can be set up to measure the time between a transition in pulses. So if the voltage goes up and then goes down, the 2 transitions of going up and go down can trigger this timer, start it, stop it, then an interrupt occurs, and then you can read the value and work out how long the pulse lasted for. So that's our circuit, and then we'll go on to explain the software.
We are now going to write 2 programs. The first to detect the gate interrupt.
Okay, so we're going to set up the configuration for our project using MPLAB. So it's a new project, standalone. We're going to use the PIC 18F25Q10 microprocessor. We're using my PIC kit 3, my old trusty PIC kit 3. We're using XC8, it's the C program provided by Microchip. and we're going to call it DCC underscore decode. Okay, set as our main project. Let's finish. Right, we're going to use the code configurator, so it allows us to set all the registers up and that for this thing to just start up and get ready. So we'll click on that and wait for that to load up. And the code configurator, we're going to save it, the configuration as a file. So we'll call this as well DCC decode. Right, so we're going to use the internal high frequency oscillator, and we're going to 64 megahertz. The internal oscillator runs 64 megahertz. We got the watchdog timer disabled. We don't want that. What we do need to do, which I keep forgetting to do, is this brown out reset voltage. If you leave it at 1.9 volts, it will cause a problem when you compile the project. So I'll just set this up to 2.7 volts. It's happy with that. So that's fine. We're looking good there. I'm going to put RC3 here. There's an LED on that, so we're going to drive that as an output. So if we go to general purpose output RC3, you can now see that that's our output to drive the LED. Let's get our gate function working now. So it's part of one of the timer functions, timer 1. So we add that in. The clock source, we're going to make it FOS divided by 4, so it runs about 16 megahertz. We're going to enable the gate. When we enable the gate, what we've got is it comes in on T1G pin there. So that's where we connect our DCC signal. And then this will measure the period. And so we enable the gate single pulse mode. And when it's detected a pulse, i.e. it's detected an edge going high and an edge going low, we will then interrupt and run a program in the interrupt handler. So that is the setup procedure. Oh, before we do that, let's just have pin module a minute, because I want to make sure that our RC3 switch the analog side off. We don't want that. Now we've done that, we will need to generate all the code that will do this. So we'll generate our code. Yes. Yeah, okay, I know what that is. So we'll say no. We'll go to timer module. Got 2 seconds in there. It doesn't really matter what's in there at all, really. But I'll put 2 milliseconds in there, then it'll be happy. So let's generate. That's better. Generation complete. So we don't need the code configurator anymore, so let's close that down. Right, the code configurator will have generated a main source file. So if I open the source files, main there. Also, it's generated these files. So, interrupt manager, timer manager, etc. But we go to main. And we go down to the main program. So we got to enable the interrupt, a global interrupt. And we got to enable the peripherals. So we've got to enable that as well. So those programs are what have been generated by the code configurator. Now what I need to do is I need to go to the timer, because the timer has to be kicked off, ready to gate the pulse. So what I need to do is enable that. So somewhere down here, here we go. Start pulse acquisition. We could just write this code, but I'm going to do it as the code configurator does it. So I go back into main, and we can do that down here. Control V. So that's the main program. We're not going to do anything else with the main program. Okay, so now we're going to look at the interrupt. So we go to interrupt manager. There we're going to call, when there's an interrupt, we're going to call this interrupt, which is in timer 1, because that's where the interrupt is. So there you are, there's our interrupt. And we're going to just toggle the LED. So we're going to lat C bits. Oops, what's happened there? Lat C bits dot RC3 equals not port C bits dot RC3. Okay, so that will toggle the LED every time it comes into an interrupt. We've cleared the interrupt flag there, that was already in the program. We need to, well, we don't need, yeah, so we need to start the acquisition again. So there we are, we need to do that again for the next pulse. And that's it, that's the program completed. The next stage is to download it to the microprocessor. So we have the oscilloscope connected. So the magenta signal is the filtered DCC signal from the Hornby Select. And then this LED is connected to the yellow display on the scope. At the minute there's no program, so we load our first program. I just got to hit the download button, and so there we go. All this is demonstrating that we've actually got an interrupt happening on the pulse width. So I'm going to single shot it and open it up. And what we get is every time there is a positive transition, the LED is toggled. So we know now that our interrupt program's working. The next stage is to make the program decode the pulses into noughts and ones.
we have to calculate the time one value for a one data bit.
So we've got to work out what numerical values we expect from timer 1 when it detects a pulse. And we want to do it for a pulse width of 1 in this example here, which has a value for 52 to 64 microseconds. So if there's a pulse detected within that range, it's considered to be a 1. So we know that when we did the configuration, we made timer 1 oscillator source a quarter of the main frequency, which is 64 megahertz. So the timer 1 is driven by a 16 megahertz clock. So let's work out the pulse width for each numerical value increment in timer 1. So if we take 1, divide that by 16 megahertz, and we get 6.25 to minus 8 seconds, or 62.5 nanoseconds. So let's see what the number is for the lower end of the window, which we can accept as a pulse width of 1, which is 52 microseconds. So let's clear that. 52 microseconds divided by 62.5 nanoseconds as a value of 832. So if the value is greater than that and less than the next number that we're going to calculate, then it is a 1 pulse. So let's calculate the higher end. So once again we have 64 microseconds divided by 62.5 nanoseconds, and that's 1024. So we've worked out now, if we put these two values in, that if the timer 1 is red and the value is between 832 and 1024, we know it's a 1 pulse.
We can now write a second program to detect a 1 data bit.
Okay, so we've just toggled the LED every time there's an interrupt, but now we need to decode the signal. So we're going to filter out the noughts and ones. So if I'm just going to copy in this piece of program, already got that one. So what I'll do is I'll take this one out. Okay, so we're actually now going to read the timer value, and then we're going to clear that timer value, and then we start the next cycle waiting for the next edge, and this is where our period comes in, and as we know, we worked out just now, it is 832 and 1024. And what we'll do is we'll switch on the LED if the pulse is in that period, which is then the 1 pulse. If not, we'll assume it's a 0 pulse. And in fact, I got the start acquisition from the other one, so I'll take this one out. Actually, we don't need that one there. Okay, so let's give it a go. So we're going to download this and see what happens. Okay, so we've just downloaded our new piece of program, and there we go. So let's do a signal. So we've got here, yes, actually I'll do another single shot on that. So whenever there's a 1 pulse, the LED should be high, and whenever there's a 0 pulse, the LED should be low. So we got here is a 0 forcing the LED low, and then a 1 forcing the LED high. So it's working. We are in a position where we have detected noughts and ones, which is brilliant. What we actually found, because we're not using a crystal oscillator on the microprocessor, so there could be errors in the frequency at which it's running, which will affect the timing period. But we did have a look at that, and it was a small error in the timing period, but not enough for a simple circuit like this to be worried about it.
And on next video, we are going to write a program to decode the home page select data stream. If anyone wants further information on what we've covered so far, please leave a comment